free cooling. We're going to cover it both from the water and the air side. I'm going to try to cover the issues around air side free cooling, and Chris will be carrying the water side on the second half of the program. Let's take a look at what we expect. And of course, within the water side, Chris will cover that, as I said. Within the air side economizers, there's two basic types: direct, the so-called fresh air cooling, and indirect, which involves isolating the air via an air-to-air heat exchanger. Before we go down that technical path, we really want to take a look at a little bit of where this airflow standard, our environment in our data center, our proverbial mission-critical data center, was first defined tightly by the ASHRAE TC 9.9 committee and released as a 2004 standard. It's basically the Bible of the industry, and we'd like to keep our data centers at the nice recommended temperature, 68 to 72 is our preferred area of operation, with nice tight humidity parameters in the 40 to 55% range. We'd like to keep it really tight at a nice 50% perfect or so-called perfect humidity and control the variations as tightly as possible. The industry has really lived with that for many, many years, and in fact, obviously predates that, going back to the days of the mainframe. And as a result, we've pretty much, fixated on that 70-degree, 50% humidity number for the last 30 or 40 years. Equipment has changed radically since the days of the mainframe and paper tape and punch cards and such, and frankly, a lot of the humidity specs in particular relate back when we used to process tons and tons of paper, both for punch cards for the input and reams of paper for green bar printouts that used to all reside within the same data center space. Within that next concept, we decided that TC 9.9 was replaced in 2008 with the second edition. Now, the first one in 2004 was the first edition. And a couple of changes took place there. The temperature broadened slightly out to 80.6 Fahrenheit. But more importantly, the place where we measured the temperature, which was typically in the room, was now sort of focused on the fact that our servers were really the critical issue, meaning all the IT gear, not just necessarily servers. And we needed to take the intake temperature of the equipment rather than the average room temperature. The humidity range was broadened slightly, which was fine, but that subtle change, which was really not the focus of that and was overlooked by many, is really key to how we can control and better, ensure proper thermal compliance to our equipment. Along came that update, but people never really followed that update. There was still that traditional outlook. People felt, still comfortable keeping it at 70, 72 degrees. So even though as far back as 2008, no one pushed that envelope to the broader temperatures. In 2011, ASHRAE released basically a reissue of Class 1 and Class 2, and renaming it as A1 and A2. The recommended temperature envelope still remained as it did in 2008, to 64 to 80.6 degrees, or of course if you're working in Celsius, which is what the document is originally written in, 18 to 27. This was broadened, it was remained from 2008, but what happened is, and this is kind of the interesting thing, we've always talked only about the recommended ranges. The reality is there always was an allowable range, and what we need to really look at is, what is the equipment capable of operating at? We always felt safe in the recommended range and tended to ignore the operating range, but Class A1 allowable is essentially almost to 90 degrees, 89.6. Within Class A2, which is something we never really talk about, but in fact exists, we can go to 95 degrees Fahrenheit. And notice also that in both A1 and A2 allowable, our permissible humidity ranges is 80 to 20% or 20 to 80% non-condensing relative humidity. A radical difference from the proverbial target of 50% RH with plus or minus 5%. And kind of more interesting if you look at the equipment that's been manufactured for the last 5 to 7 years now, or actually that says 3 to 5 in the slides, more like almost 7 in many cases, going back to 2005, you'll see that a typical server from any of the major OEM brands will typically be rated at those particular numbers of 50 to 95 degrees Fahrenheit and 80 to 20% relative humidity. The only exception to that area is going to be that of tape. Tape is a little more sensitive, in fact, to humidity changes because of its mechanical nature and sudden changes in temperature. But nonetheless, we've sort of ignored those numbers. We've always lived in that Class 1, now Class A1 recommended range, and people are sort of reticent to do that. ASHRAE went a little further in that white paper, and essentially they began to state that the world did not end when you move that temperature dial away from the 72-degree mark. And they went a little further and added 2 additional classes to that category called A3 and A4. And quite shockingly, you're talking about temperatures of up to 104 for A3 equipment with up to 85% relative humidity. And in A4, we're talking about 113 degrees with up to 90% relative humidity. This was basically a consortium of manufacturers of IT gear, not just mechanical engineers. So this really depends on the ability of the OEMs to deliver equipment that will operate in those temperatures. Now, prior to the existence of these higher ranges in the ASHRAE guidelines, basically this was a reflection of the telco industry and the NEB standard, which allowed for equipment to operate in desert shacks or in Alaska with very little heating and cooling and a very, very broad temperature range. Telco's, the originator of the 5.9s, and they've been building equipment to that kind of specifications all along. We've been sort of babying the data center and, trying to match the reliability of telco and the proverbial 5.9s, and yet they've been doing it for a much longer time. In essence, the ASHRAE 2011 document speaks of going to data centers with no mechanical cooling where locations allow that. And so we really have to say this is what's driving this whole movement towards free cooling. All right? It really is there a question of location where you can support this, and we're going to examine that a little more closely with the air side. And water side, of course, is also going to offer you many opportunities for free cooling. Let's take a closer look at the air side for a moment. Direct air side economizers, even though we think of them as sort of a total reversal of what we'd like in the data center, is being explored by a number of major organizations. In point of fact, NetApp was actually the first Energy Star data center, and the data center program was run by the EPA for the most efficient data centers facility side, I should say. That first site was in North Carolina. We're going to take a look at that in a minute. Yahoo's got the chicken coop in upstate New York. Facebook made some headlines with their Prineville, Oregon data center. And if you want to go to the opposite end of the spectrum, Deutsche Bank has a pilot project that was commissioned last year in Metro New York area that's running live data on their financial side using free airside economizers, direct air injection into the system. And they're looking at some really, really aggressive numbers, yet they are a financial organization rather than a social or search engine. Now, they're looking at different aspects of it. The bigger problem, of course, is the fact that if we're going to introduce outside air, we've got to worry about filtering it for particulate matter. And, of course, we'd like to control the humidity within even the recommended or the allowable ranges without spending an inordinate amount of energy doing that on mechanical cooling by dehumidification. Clearly, part of the direct philosophy is allowing broader temperature and humidity ranges. And we have to get accustomed to the fact that, newer equipment today is pretty rugged when it comes to that. If you're looking at legacy data centers with legacy equipment, you have to go back towards the recommended ranges. If you're talking about new equipment as the prime occupiers of the white space, then it allows us to explore more and more broader temperature ranges for free cooling. On the indirect side, we've got a number of mechanisms to allow us to look at air-to-air heat exchanger, Kyoto wheel. Other manufacturers are offering all sorts of custom air-to-air heat exchangers. Different standard manufacturers are beginning to offer them as well. Let's take a quick look at the NetApp. NetApp, which is an audited one-year study for the Energy Star for Data Centers Award. Basically, in July of 2010, completed 12 months of recorded data that was submitted and certified to the Department of Energy and the EPA. And they did an average of the 74 Fahrenheit supply air, but they allowed it to go to 75% relative humidity. And remember, this is prior to the 2011 ASHRAE new temperature ranges. And they really allowed it to operate and prove out that the equipment could operate this. In their case, they used cold aisle containment to maximize their airflow. Their result was that in North Carolina, which is a relatively humid environment, they ran at 60% of the time 5,800 hours of free cooling in a year, just using fan energy without ever touching a compressor. And they had an annualized PUE of 1.35, meaning that they went and completely annualized that. It wasn't a spot worst-case condition. And they proved out that a large company can, in fact, operate on airside free cooling in a part of the country that has wide temperature ranges, wide humidity ranges, and have done so successfully for the last 2 years. So to take a quicker look at the pros and cons, we're basically looking at the direct method of fresh air. It gives us the widest opportunity for free cooling. The cons are, of course, you're bringing in outside air, which in many cases can contain some particulate matter, possibility of smoke induction, and corrosion if you're near sources of impure air. It's a little bit difficult to retrofit in a new data center, but certainly in a new build there's a tremendous opportunity for energy savings. Indirect gives us the advantage of having a no outside air system, basically a closed loop similar to what we do. And it does not really require any additional special dehumidification other than what you'd already be using in a closed loop system. The downside to it, of course, an air-to-air heat exchanger does not give us as much effective opportunity to cool as a fresh air heat exchanger, but nonetheless gives us that separation of outside and inside air. The other penalty to it, besides a slightly narrower temperature range, is that we now have to have higher fan energy. We have basically twice as many fans. The fans that are normally circulating the air within the data center, plus we have to drive air through the air-to-air heat exchanger, which gives us additional fan energy compared to a direct airside economizer. Of course, this still is the elimination of chiller time, but we do not have as much energy gain as we do from the direct system. For a quick look at where we're at, traditional cooling methods, we're a closed-loop system. We introduced the minimal amount of outside fresh air other than makeup air for human purposes. We use cracks or crays, computer room air conditioners, or computer room air handlers. And, of course, it cools the interior air from the return air side of the cooling system. We've typically moved to a hot aisle, cold aisle system, which, while in a general condition allows some minor mixing, of course, the less mixing the better, and there's various techniques for controlling that. So if we look at our traditional closed loop, the most common one still is a open return path between the cabinets and the hot air trying to get back to the cracks. And while we could probably make a 2-hour webinar out of just airflow management, this is a simplified view of the open return. We're going to take a sort of a little bit better look at that, where we're adding some return ducting or plenum to try to capture as much of the hot air and move it back towards the crack or cray. And notice in these next few drawings, I've just used the term crack generically. For computer room air conditioner, the same would apply basically if these were water-cooled crays. So effectively, it's just a cooling unit for purposes of airflow example. Now, in this case, we're talking about looking at the loop maintaining A1 recommended 64 to 80.6 degrees Fahrenheit. And this is the typical closed-loop system using a raised floor. Effectively, we're pushing the air into the floor just like any other traditional data center, except we're now trying to look at containing the return air a little better and bringing it directly back into the cooling unit. And we've got the number of 100% under the word crack there, just to indicate that effectively all the air has to pass through there and be cooled by the crack. We have no real opportunity in this particular drawing to show any free cooling. Also, I'd like you to take note of a typical condition where we're saying that we're going to try to maintain within the ASHRAE envelope of 80.6, so we're looking at 80 degrees or less in the cold aisle. And we're using a typical 20-degree temperature rise, which is obviously varies from the type of equipment for the next few examples. So if all things were perfect, we'd bring in 80-degree air into the cold aisle. We'd have a 20-degree delta T across the servers, which would result in a 100-degree Fahrenheit return to the crack. Of course, this is really not the case in most data centers, but it would be a nice example of how we could still maintain ASHRAE recommended and optimize our closed-loop system. Let's take another look at that as if we were going to introduce fresh air. Now, this is not the ideal or perfect scenario for an outside economizer, but I'm just using this layout to compare it to a traditional system. So we're showing a traditional crack or cray in its exact same location, but now what we've done is we've created an air box on top of that plenum that allows for the cool air to come in on the left, and we're able to exhaust the warm air off on the right. Now, it's a hypothetical construction. You'd probably not want to use an additional traditional crack in there and probably use a roof side air handler, but nonetheless, to compare the two, I've laid this out in this fashion. So we're showing in this case outside air is running at 80 degrees Fahrenheit, again within the limit of ASHRAEs. We're not even stepping outside to the allowables, just keeping it within the 20-degree, within the recommended window. And so we're showing 80 degree or lower air entering on the left. It's being directed by the fact that the vents and fans on the top side units are directing the air into the cooling unit, but notice it says the crack is off. We're basically pushing the entire airflow from the outside through the unit into the floor, essentially using only the fans to push that air. The crack is off at that point. Again, we're keeping the cold aisle temperature there at 80 degrees, same 20-degree temperature rise. So now that 100-degree Fahrenheit air is now pushed up and out on the other side of the building. You can use a combination of dampers with fans, or any number of the control mechanisms to do that. And you can see easily how, as long as the outside air is under 80 degrees, there's no need to run the compressors in the crack or the cray or operate chilled water. Let's take another side look at that. All right. So now, again, we're now looking at the fact that we've now got 60-degree air outside, and we don't want to go below the bottom of the A1 recommended range, which is 64. And what we're going to do is we're going to begin to partially open the dampers. If you look on the left-hand side, you'll see that we've got some mixing of air between the outside air and the inside air. So now we've got a blended air coming in at approximately 65 degrees into the floor air. And, of course, now we have a 65-degree bottom to our cold aisle. Again, we're showing a 20-degree temperature rise, which means we've got 85-degree air up in the vents, and we're partially exhausting some of that to make sure we have a balanced airflow. So I think everyone can understand that if the air is within that range, we easily can meet the A1 recommend. Now, of course, we can continue this all the way down 60 or less, so we can go to 50, 40, 30 degrees, etc. on the outside air. And depending on how we use that mixing box, we simply can keep mixing the warm return air with the outside air to the point where we keep the air at 65 or lower. And so we may be down to almost no inside air when it's freezing outside, no outside air when it's freezing outside, and mostly recirculated. But as long as we're able to control the mixing in that left-hand portion of the air box, we're able to regulate the temperatures from 80 degrees on down without any mixing of air, without any mechanical cooling. And so let's take a next step. What happens at higher temperatures? We've seen already that at lower temperatures we can directly use outside air. The trick is going to be to see what happens when we have outside air that's higher than the other temperatures. We can still go for partial free cooling. All right? As long as we're able to eject the hotter air than that which is in the return air, we have the opportunity to do partial free cooling. And so in this example that we've used before, we're still going to keep the supply air again within ASHRAE recommended at 80 degrees. We're going to keep that 20 degree delta T, and our IT is at 100. However, the outside air is 90. So let's say take a look at that. Notice that the fact that the outside air at 90 is lower than the return air temperature. It is still less energy intensive for us to bring 90 degree air past that crack than 100 degree return air. So we can still use less energy, and we're getting partial free cooling on that crack unit. And again, it doesn't have to be a crack. Then the recommended 80 degree temperature and the 100 degree return. So it is possible to run hotter air outside and still maintain free cooling. As long as your return air temperature is hotter than the outside air, you still can get partial free cooling. So here's an example. Okay, once we've broken through the temperature barrier, now we've got 105 on the outside. Clearly, we shut off all the outside air, and we now cycle the recycled air back to where we started, and we're running purely on 100% internal air. Now, of course, one of the things that will allow us to do this is a number of ways, including variable speed fans, which gives us a tremendous opportunity for free cooling, or for energy saving, I should say. And as you can see from this chart, by lowering the fan speed, we still maintain a great deal of the airflow, but at a tremendous reduction in slope on the fan speed. And I believe Chris is going to spend a little more time on any variable speed drive as well. So adiabatic cooling basically is the injection of moisture into the air, and it allows us to cool it without any mechanical cooling. It can be done with either direct or indirect, and I'm going to let Chris cover some of that as well. It's an old technology going back to the days of the swamp cooler. Humidity control, of course, is concern to all of us, and it does require mechanical cooling and dehumidification. It's very common to have battling cracks. It's subject in itself. So even if we're using outside cooling or inside cooling, we do want to try to broaden the envelope and not have battling cracks. Essentially, we want to try to minimize the number of units that are rehumidifying and dehumidifying simultaneously in a room. But if we're doing outside air control, we're going to have a centralized control system. And finally, let's just take a quick look at under the older ASHRAE guidelines. We're looking at the green grid as a source of information here. And their 2009 map, which was a reflection of the 2008 ASHRAE A1 recommended standard, shows the number of hours in a year that you can achieve some free cooling. If we look at the next map, which was a revision, an update based on the 2011 ASHRAE guidelines, you can see how virtually the number of hours have really moved past that, as long as we can stay in A2 recommended range, which is up to 95 degrees. That blue area is basically all 100% cooling at this point. And even places like Miami allow for 5,000 hours a year of free cooling with airside economizers, direct, of course. And finally, if we were to look at A3, which is the next generation of equipment that's pretty much coming out this year and next, you can see how the entire U.S. and Canada is completely covered by this blue area, meaning we could go to 100% free cooling with A3 equipment. So to sum up, the 2009 Energy Star program discovered that the majority of data centers pretty much came up with a PUE of 2, the proverbial number that's quoted by everybody. But with the advent of free cooling, we really can see how we can bring our PUEs down, way down in the 1.2, 1.3 range easily without any extreme methods by using outside free cooling. And the next question that always everybody asks is, so what is the safe temperature? Well, the ASHRAE document really talked about the introduction of the X factor, which took into account broad variations of temperatures. And unfortunately, because of the limited time we have here, I can tell you I will be discussing this in my column on Mission Critical Magazine. My column is called Hot Aisle Insight, which is, I believe the issue is coming out very shortly. And so I'd ask you to please stay tuned and read the magazine on the next Hot Aisle Insight.
Right, you are, Julius, and that issue will be going to the printer today or tomorrow, and I look forward to sharing that information with everybody. Chris, I know you're on board and you have a nice presentation to come, and thank you very much, Julius.
Thanks, everyone. Let's get started. I'm Chris Kirkchin from KW Mission Critical Engineering. The agenda today is, as Julius says, on my side, is primarily water side free cooling. I will talk a little bit about variable speed drive, so we're ensured that we've covered that aspect, because the application of variable speed drives to both chiller systems and fan systems can save a significant amount of energy on your mechanical system. So our agenda, Julius really covered this piece very well, the base of the opportunity, IT operating envelope. We won't talk about that. We'll focus on water-side free cooling using cooling towers. We'll talk about how elevating chilled water supply temperature increases chilled water plant efficiency. We'll talk a little bit about integrated water-side economizers. We're using cooling towers as well as chillers in series. And then we'll talk about indirect adiabatic cooling. So Julius has already introduced the air-to-air heat exchanger. Well, let's just spray water on it and take advantage of adiabatic cooling there. And finally, variable speed drives. And as we said, Julius covered this one very, very well. Clearly, we have an extended range for supply air intake, supply air inlet into the IT equipment. And obviously, if you're able to operate your IT equipment at those elevated temperatures, we can take advantage of significantly more hours outside for free cooling. Okay, so I think this is a fantastic time to be in data center design, certainly in mechanical engineering. If you think back to 7, 8 years ago, the majority of data centers were monolithic. There were just a couple of different systems that were applied to the data center. There was very little discussion or interest in PUE and energy efficiency, and everyone said they were interested in innovation if you could show them where you had done it 15 or 16 times. And if you look at the data center market today, there's so much opportunity for innovation. There's so many different types of systems that are applied, and designers and owners are actively looking to try new things and do things differently. And in many markets, direct evaporative, direct OA, dry bulb economizers, indirect evap cooling is a bit less conventional. Certainly, there are some markets, the internet specifically, where those are much more conventional. And then on the right, you've got the more conventional systems. But as time goes by, what you're seeing is that what was less conventional is becoming more conventional, and as we apply these systems more, the PUEs get lower and lower. So let's look at water-side free cooling using solely cooling towers. Right, cooling towers create cold water when you pass the water over the tower and use adiabatic cooling. And you can take that cold condenser water and use it to perform chilled water cooling. You can either eliminate the requirement to operate the chillers, or you can minimize the requirements to operate the chillers when you use them either in series or in parallel. And unlike the dry bulb economizer, the energy savings on the water side economizer with the cooling tower dependent on the wet bulb, the moisture content of the air. So if we look at this slide here, you're looking at Newark weather data, and on the left side of the screen you're looking at the cold aisle temperature, and at the upper left you see 76-degree cold aisle temperature. And we can maintain a 76-degree cold aisle temperature with 70-degree supply water. And we can maintain or generate 70-degree supply water, 70-degree condenser water with a wet bulb of 63 degrees Fahrenheit. And in Newark, New Jersey, what you see is that you've got approximately 7,200 hours of free cooling. In other words, 72, 33 hours or less, we do not need mechanical cooling. If you're willing to take a 77-degree cold aisle temperature, then your free cooling hours climb to 74, 17, 78 degrees, it climbs to 75, 74. And if you take it all the way up to 90, the maximum allowable in the Class A1 range, all 87, 60 hours can be provided with a cooling tower. So this just goes to show how much free cooling can be generated with a cooling tower, right? We used to think of waterside economizers where you're primarily running chillers and you're using the cooling towers, or you're providing free cooling for fewer hours than the mechanical cooling. Now it's the other way around by a significant margin. And depending on what your electrical inefficiencies are in your system, right, if you're willing to accept up to a 90-degree supply air temperature, remember, you're only going to see that 90-degree supply air temperature, and this is, in this case, Newark, New Jersey, for 1 hour, right? That would be the upper limit. You're going to run at a PUE certainly less than 1.25, 1.22, 1.20, depending on what your electrical inefficiencies are, right? It's a very flat curve. It's a flat line, excuse me, right? You're running cooling towers, you're running pumps, and you're running fans, and it's just running full out to match your load. Let's talk about, before we put chillers, before we put the chillers and the cooling towers together, let's talk about chilled water plant operating efficiency and the correlation to chilled water temperature. For any piece of refrigeration equipment, you've got a temperature entropy curve that governs the performance, and Q at the rectangle in the chart is the cooling that's generated by the refrigeration equipment, and what's identified as W is the work done by the refrigeration machine. So for whatever Q you need, however much cooling you need, the refrigeration equipment has to do work. So how do you lower or reduce the amount of work that's done by that refrigeration machine? You have to increase the evaporating temperature or the chilled water temperature, and B, you've got to decrease the condensing temperature. And when you can do both of those, right, taking advantage of the cool ambient and elevating your chilled water because your IT can accept higher supply air temperatures, you can significantly lower and reduce the amount of work that's done by the refrigeration machine and get more free cooling. Well, excuse me, and get more cooling out of the machine. Right, so if you look at legacy design chilled water systems with 85-degree condenser water in the upper left corner, you see that those machines traditionally operated around 0.5, or traditionally operate at 0.565 kilowatts per ton. If you lower the condensing water temperature down to 60, you improve the efficiency to 0.338 kW per ton. Increase that chilled water temperature to 55, right? At 85-degree condenser, your chiller efficiency improves to 0.43. You lower the condenser water temperature to 60, you're down to 0.256. And if you move to 60-degree chilled water temperature, right, you start to see chiller efficiencies in the 0.3s to 0.2s to 0.3 kWs per ton. But a general rule of thumb is you see a 5% improvement in chiller efficiency for every 2 degrees Fahrenheit increase in chilled water. You see a 19% improvement for every 10-degree decrease in condenser water temperature. Part load efficiency curves, right? If you apply a variable speed drive to your chiller, you significantly improve the efficiency of the chiller. Over at the right side, you can see that the purple line and the blue line intersect when those chillers are both operating at 100%. You see the 0.565 kilowatts per ton. But if you apply a variable speed drive, 30%, 40%, 50%, 60%, it's a real sweet spot on many machines, and you can significantly improve chiller performance, right? You're under 0.3 kW per ton. right? And this is applied at conventional chilled water temperatures. You start applying the variable speed drives at elevated temperatures, your chiller efficiencies are even better. Okay, so let's talk about putting the chillers. Let's talk about putting the chillers together with the cooling towers with water side economizers. And by integrated, I mean a series water side economizer. So if you want to operate with this type of system, you need to be in an area where you have a lower wet bulb. Ideally, you've got 7 to 10 degree approach for many hours, where your wet bulb temperature is 7 to 10 degrees less than your chilled water temperature. Certainly elevating your chilled water temperature extends your hours. And here's how that series capable water side economizer works. You've got your water coming back from your data center, chilled water return. It's passing through a pump, and when you can use the cold condenser water to create chilled water, you open the valve to the heat exchanger. That water comes out of the heat exchanger. If it's fully capable of meeting the load, you open the valve that says full economizer and send that water out to the load. If you need to get some more cooling out of that, if you need to cool that condenser water further, you open the valve that says partial economizer, send the water to the chiller, and you're able to gain some additional free cooling. This is the series capable, or what's called integrated economizer. So on the lower left, you see chilled water temperature, traditional design 45 degrees. You can see you would need, still in the New Jersey weather data market, you're looking at 5,000 hours of mechanical cooling, 1,560 hours of partial economizer, and 2,094 hours of full economizer. Increase that water temperature to 60, you've reduced your mechanical cooling by 50%. You're down to 2,579 hours of mechanical cooling, and you've more than doubled your full free cooling economizer hours to 5,057. Your annual chilled water plant PUE, if you're looking at a 76 degree supply water temperature, you're talking average about 1.35 PUE that you're able to attain with this system with a 76 degree cold aisle temperature. And as you can see, you're running at a constant low PUE until you get to May, where you start to run your chillers, and your energy and your PUE climb up until you get back to October, where you start into more extended free cooling hours. Okay, let's talk about adiabatic cooling. In indirect evaporative cooling, the IDEC, air is sensibly cooled by the effect of evaporation across the heat exchanger. So we're taking that air-to-air heat exchanger and we're passing water over it. I know we're moving towards the 3 o'clock. I'll wrap up quickly so we still have some time for questions. There are a lot of different manufacturers of these IDECs. There's generally 2 different approaches. There's the air-to-air heat exchanger, where you're spraying water over the air-to-air heat exchanger, or there's configurations where one side of the IDEC is a cooling tower and you're pumping that water from the cooling tower over to a cooling coil. The units can be provided as packaged AHUs, or they can be provided in split configurations indoors and outdoors. Here's a picture of an IDEC unit. Inside you've got the heat exchanger, you've got on the inside tubes, you've got the air from the data center in the red, and then that air moves out to the blue, back to the data center, the supply air fan. And then you've got the wet side, where your air is introduced, in this case through the bottom, and then you're spraying water over the heat exchanger, and that hot moist air is exhausted off the top. So this is the IDEC. And with the IDEC, let's see, with 76 degree supply air, you're able to maintain around 1.27, 1.28 PUE. If you move to an 84 if you move to an 84-degree supply air and still in the New Jersey area, you're moving that PUE efficiency to around 1.2. So you can certainly maintain under 1.3, and you can get yourself under 1.2 and still maintain well within the ASHRAE A1 recommended range. Finally, let's talk about variable speed drives. Power reduces by the cube of the speed reduction. We've got a quick example with 1,500 kilowatts of UPS load and plus 2 air conditioners. So you would need 10 150 kW units to meet the load. With 2 redundant, you have 12. In each unit is assumed to have a 13 kilowatt motor. So if you're running all 12 units at full speed, you're looking at an annual cost of $136,000 per year. If you run all 12 units at 80%, your cost is reduced almost in half, down to $69,000, right? Because you're reducing your energy by the cube of the speed reduction. If you take those 12 units and operate at 60%, your fan energy drops to $29,000. And certainly, so many data centers operate at part load. Retrofitting variable speed drives onto constant volume fans in data centers that are operating at part load is a fantastic way to immediately reduce energy savings in your data center. And with that, I've closed it out, and we still have 10 minutes of Q&A before our 3 o'clock.
Very good. Thank you. Thank you very much, Chris. And you're right. In fact, we have maybe even a little more than 10 minutes. So we'll get to as many questions as we can in that time. And the first one is, with air side economization, do you have to provide UPS power for fans, understanding that we have no standby time with air? Julius, that was directed during your part of the presentation, but I'll ask you both to comment on that.
Yeah, okay. Well, certainly the short answer to that is it's very difficult, obviously, with a crack unit, that is one with a built-in compressor, to power that from UPS, but it's not uncommon to power chilled water units with fans using the UPS to maintain the fans. The real critical question there is at what density is that data center running? And so as you begin to move up the densities, and you can either speak in terms of watts per rack or kilowatts per rack or watts per square foot, the time to live really radically falls off as you really move past the higher densities. Once you go past 3 or 4 kilowatts a cabinet, you start to roll off quite quickly in the number of minutes it takes for the temperature to rise. And so in looking at any high-density solution, we typically want the fans to run if you have a chilled water system, and also the pumps to run to use the mass of the water that's either in the pipes or hopefully an auxiliary chilled water tank to give you that ride through. If you have no...
This is Chris. Let me add one thing to that quickly, and I would say density is important, but also what's equally as important is the supply air temperature. So what I would answer that question, I would say yes, it is important to put those supply air fans on variable speed drives, on UPSs at elevated temperatures, yes.
Chris makes a good point. Obviously, to the safety number, you know, the higher you ride that ASHRAE curve, the less time you have to that critical temperature. So one of the advantages of keeping the ASHRAE recommended, of course, you had more time to live because your temperature started at a base temperature of 68 or 70. On the other hand, if you're going to keep your air temperatures at 85 or 90, your time to that cutoff number is far reduced. So good point, Chris.
Okay. The next question, and I'll again direct it to both of you. Are there condensation issues or challenges in the mixing box when the delta is high?
Okay, so the delta T between the hot air coming back from the return versus the cool air coming in when we're mixing, there are some condensation issues, and in my drawings we did not deal with humidity issues. Typically, you will have a coil which will be in front of that as a dehumidification coil in the event that you want to trim the humidification, which is probably a lot more cost effective than running the main cooling coils. So it is a form of mitigation, but certainly a coil just capable of pulling the humidity out has a far lower energy requirement than a full cooling coil.
And Chris, any thoughts on that one?
Yeah, I would say in what you're seeing now is you're seeing that humidification is minimally applied to the raised floor or to the computer room. Many climates don't require it. You're seeing very little application now of humidification to the data center. Certainly, you need to pay attention to mixing box design. That's good practice. But generally, the air is fairly dry in the data center, and condensation is not that much of a concern. Certainly, I think you have the concern on the high side, right? What do you do with your airside economizer if you have a hot, humid, raining day? How do you address that, right? Do you go to free cooling? Excuse me. Do you go to refrigerated cooling, or do you turn off your free cooling? I think that's just as big a concern as the other side of the equation, the cold condition.
Okay. Chris, this next question came in during your portion of the presentation, and it relates, strictly speaking, to cooling towers, although perfectly happy to have Julius tackle it too. How do you feel about claims from water filter manufacturers that their products can help you achieve substantial energy savings in the cooling towers?
Yeah, right. So I would say that those products are not about reducing energy. They're about reducing water consumption, right? And water in some areas is just as valuable and just as expensive as a commodity as electricity. So I would say certainly pay attention to your chemical treatment or whatever alternative treatment you're providing for your cooling tower, and focus on water reduction as much as possible. Certainly, you need to protect your media from dirt, from contamination, from corrosion, right? Because if you clog your cooling towers, if you don't keep your cooling towers clean, then you can reduce energy efficiency and reduce some of the heat transfer. But primarily, you're concerned with water treatment and reducing blowdown.
Julius, any thoughts on that one?
Well, obviously I concur with Chris on that. The problem, of course, with all cooling towers is maintenance, which is one of the things that, is true whether using economized or uneconomized situation. So, by allowing a chemical to help you lower your maintenance hours or, the performance reduction as the buildup occurs, it does effectively give you some gain. Of course, each product has its own set of advertising, gains versus real gains, and only actual operating experience will prove that out in a particular climatic situation.
Okay. Julius, during your talk, you cited a couple of recent applications, and in the case of Deutsche Bank, you pointed out it was a financial and drew a distinction between it and some of the others. Are there different considerations, and I'm going to ask this of you as well, Chris, are there different considerations between different types of applications when we start talking about some of these cooling techniques as we've been discussing today?
Well, I think that's you just hit the nail on the head, and that is the fact that the internet search, social media types such as we cited, such as Yahoo, Facebook, etc., have the proverbial luxury of shifting that compute load pretty much at will. It's not a transactional load. It is a query request. And so if you lose a server at Google or Yahoo or anyone else because you did a internet search query, the customer is really not paying for that search. It's just assumed that when you go to that search engine, you'll get an answer. And frankly, if you have to click again to send the question because a server that you were on failed, it's being, basically shifted that web request over to another server or frankly to another site, depending on the level of fault tolerance. If you're in a transactional environment such as a bank or any other financial organization, they're not just blindly shifting over requests. They're dealing with actual live financial transactions. And so the risk-reward ratio there is far less tolerant in a financial organization than in a public media search. So part of the architecture of the Googles of the world is the fact that it's a free search, and we can afford to shift that in case we have a failure, which totally affects how the building is looked at.
And Chris, what about the distinction between various application types?
No, I agree with what Julius has said. It's interesting that he brought up that example, the Deutsche Bank example. I was at a Deutsche Bank presentation at the Uptime Institute 2 weeks ago, where they unequivocally stated that they see no reduction in reliability using outside air in Manhattan, right? And they've got the data to back that up. So I think it gets back to my earlier point that what was less conventional is becoming more conventional, certainly for some of the clients and end users who 5 years ago would never have ventured into the outside air realm. It's a good question.
Very good, very good. Thank you. Now, now we're out of time, as it turns out. So this concludes today's webinar, and I'd like to thank you, Chris and Julius, for terrific presentations and a good Q&A session. I'd also like to thank our sponsors, Aquatherm and CoolSim. As you exit today's webinar, please take a couple of minutes to complete our survey by clicking on the survey icon in the taskbar. We strongly welcome your detailed comments to help us serve you better. If you have any additional questions or comments, please don't hesitate to contact webinars@bnpmedia.com.